You've probably wondered how a massive site, say like Twitter, can handle thousands of tweets every single second without crashing, right? Well, it all boils down to one word: scaling. And that's exactly what we're diving into today. We are going to break down one of the most common and most important system design interview questions out there. How do you take an application from just a handful of users to millions? So here's our game plan. We're going to start with the most basic setup and its biggest problem. Then we'll tackle each new bottleneck as it pops up. First, we'll solve the traffic jams. Then we'll figure out how to keep our data safe. And finally, we'll inject some serious speed into the system. And by the end, you'll see exactly how all these parts click together. All right, let's jump right in. Section 1, the scaling challenge. Picture this. We've built a fantastic new app, but its entire universe, it's all running on just one lonely server. So imagine your app is a huge hit. Users are signing up like crazy. But remember, everything, the website, the database, all the code, is on that one machine. So what happens when you get that massive surge of traffic? Or even worse, what if the server just dies? Yeah, the answer is pretty simple and honestly pretty brutal. You have what's called a single point of failure. If that one server goes down, your entire app is offline. Poof, gone. And for any app that wants to be successful, that's just not an option. We absolutely have to build in some safety nets, some redundancy. And our first step is to deal with all that traffic. So how do we fix this whole traffic jam situation? Well, we introduce our very first super important component, the load balancer. Okay, so what is a load balancer? The easiest way to think about it is like a traffic cop for your application. It stands in front of a whole group, or a pool of web servers, and its one job is to direct incoming requests evenly between them. It could do this in a simple way like round robin, one for you, and one for you, or it could be smarter and check which server is the least busy. But either way, the goal is always the same. Make sure no single server gets buried under a mountain of requests. Now, this setup here shows a really critical change in our architecture. A user's request doesn't go directly to a web server anymore. Instead, it hits the public IP address of the load balancer. The web servers themselves, they're now tucked away on a private network with private IPs. This is huge for security. It means they're no longer exposed to the public internet. The load balancer is now our gatekeeper. It's the only way in. So let's walk through the new request flow step by step. First, your browser asks for the site, and what it gets back is the load balancer's IP. Cool. Second, the request hits the load balancer. Third, and this is important, the load balancer quickly checks which of its servers are healthy and online, and then it forwards the request to one of them, say server 1. Finally, that server does its job, processes the request, and sends the response back. And the best part? The user has no idea all this magic is happening behind the scenes. Okay, so if you're in a system design interview, these are the benefits you want to hammer home. First, you've got high availability. If one of your web servers goes down, the load balancer's health check will catch it and just stop sending traffic there. Problem solved. This makes your whole system way more reliable. And maybe most important of all, you've now got scalability. As you get more and more users, you don't have to buy a bigger, more expensive server. You just add more cheap servers to the pool. That's horizontal scaling, and it's a game changer. All right, awesome. Our web servers are now reliable, and we can scale them out. But you know how it is in system design. We've just solved one single point of failure, and in doing so, we've revealed the next one. Now all our web servers are pointing at a single database. That's our new bottleneck. So let's fix it. The solution here is something called database replication. And it's pretty much what it sounds like. We're going to create and manage multiple copies of our database. The most common way to do this is with a setup called master-slave, or what's often called primary replica these days. The idea is you have one main database that's the source of truth, and then a bunch of copies that just mirror everything it does. This little trick is a huge win for both performance and reliability. And this diagram shows you exactly how it works. You see that master database? It handles all the right operations. So when someone signs up for a new account or posts a new photo, any change to the data, that goes to the master. The master then replicates or copies that new data over to all the slave databases. The slaves, on the other hand, handle all the read operations. So when you're just browsing your feed or looking at a friend's profile, you're hitting one of the slaves. And this separation of duties is the secret sauce. Think about it. Most websites have way more reads than writes. You browse 100 things for every one thing you post. So by splitting them up, we can spread that massive read load across tons of slave databases. We're horizontally scaling our reads. The writes stay centralized on the master to make sure our data stays consistent, but our ability to handle people just looking at stuff, well, that can now scale almost forever just by adding more replicas. So what are the big wins here for your interview? First, you get a huge performance boost because all those read requests are happening in parallel. Second, you get much better reliability. Your data isn't in just one place anymore. If one server gets destroyed, you have copies. And third, you get high availability. If the master database suddenly dies, an automated process can just promote one of the slaves to be the new master, and your app can get back online with very little downtime. Okay, our system is getting pretty solid now. It's reliable, it's available, but you know what users always want? Speed. They want things to be instant. And hitting a database, even a fast replica, still takes time. It involves reading from a disk, which is slow. So it's time to add a turbocharger, a speed layer. It's time to talk about caching. So what exactly is a cache? Just think of it like your system's short-term memory. It's a temporary spot where we can store the answers to common questions or frequently accessed data. And here's the key. It stores this data in memory, in RAM, using tools like Redis or Memcached. Accessing RAM is thousands of times faster than accessing a database that has to read from a physical disk. It's a massive speedup. So where does this cache live? Well, it sits right between our web servers and our database. It's like a super fast middleman. And we're going to introduce a new golden rule for our application. From now on, before you ever go to the database to ask for data, you have to check the cache first. Let's trace how this actually works. Okay, a web server needs some data. The first thing it does is ask the cache, hey, do you have this? If the cache has it, that's what we call a cache hit, it sends the data back immediately. Super fast. Done. But what if the cache doesn't have it? That's a cache miss. No problem. The web server just goes to the database like it used to. It gets the data, but before it returns the data to the user, it makes a quick stop and stores a copy in the cache. Why? So the next time someone asks for that exact same piece of data, it'll be a super fast cache hit. Now look, caching sounds amazing, but it's not a silver bullet. You can't just slap a cache on everything. You need a strategy. Caching is perfect for data that gets read all the time, but doesn't change very often. Think of someone's profile page. You also have to think about an expiration policy, right? We need to tell the cache how long to hold on to data before it gets stale. That's called a time to live, or TTL. And finally, you have to worry about consistency. What happens when data changes in the main database? How do you make sure the cache gets updated or cleared out? These are all key things to consider. Okay, let's take a breath. We've added a load balancer to handle traffic. We've replicated our database to make it reliable, and we've just added a cache layer for lightning speed. It's time for the grand finale. Let's put all of these pieces together and see what our complete system looks like. And there it is, the whole shebang. This is what a modern, scalable architecture looks like. You can see the request coming in from the user, hitting the load balancer, getting passed to a web server, which then talks to the cache, and only then, if it has to, talks to our replicated database system. This is the blueprint. But to really lock this in, let's do one final trace. Let's follow a single request all the way from the user's browser, through every component, to the data, and all the way back. This will really show how everything works together. All right, here we go. A user's request comes in and hits the load balancer. The load balancer passes it off to an available web server. The first thing that server does is check the cache. Now let's say it's a read request and it's a cache miss. The server then goes and reads the data from a slave database. But what if it's a write request, like a new post? Then the web server talks directly to the master database. And as soon as that write is complete, the master database automatically replicates that change to all the slaves, keeping everything in sync. So there you have it. You've now got the fundamental building blocks for a really scalable system. But here's the thing about system design. You're never really done. Every time you solve one bottleneck, a new one eventually shows up somewhere else. So my question to you is, looking at this system, what would you tackle next? What's the next potential weak spot? Maybe you'd add a content delivery network, a CDN to serve images and videos faster. Or maybe some message queues to handle long-running tasks in the background. That's the real challenge, and honestly the fun, of designing systems that can truly scale. Thanks for joining this explainer.